engineers, so if everyone's in the right place, if you're not, let me know and we can redirect you. All of the surveys are in the first 2 rows, so if you could fill one of those out before you leave, that would be good because I need you to fill those out before you leave. You can leave at any point or come back if you have to. It'll be all recorded online, so if you go to the SARC website and look at our study union schedule and find the link for the YouTube video, all of it will be posted on there. And I will post the solutions for this review after the session if you want to go back and look at them, and if we also don't have time to finish the whole thing. So, any questions? The review is found either on the SARC website under Physics 1 or the Study Union website under Physics 1. Okay, is everyone in the right place for Physics 1? Okay, awesome. So are there any particular chapters or concepts that you guys are particularly want to go over? Because we may not have time to go through this entire thing.
The second chapter.
The second chapter?
Or the second, like, test material.
So, do you know what chapters that is? Okay. Anyone else? Yes?
Chapter 12.
Chapter 12? Okay, I think I have a few from chapter 12. So, anyone else? Does everyone want to start with chapter 12 then?
Okay, I didn't even teach chapter 12 in our class.
Okay,
So
that's
that
true.
may be on the exam.
I don't know. It depends on your professor. If your professor didn't teach it, I wouldn't expect it to be on the exam. Okay, so we can go over, we can just start going through maybe one per chapter and then go back through if you guys want to like have any other chapters, because we might not have time. We probably won't have time to finish the whole review, but I will have the solutions for the entire review online. Okay, so is it okay if we start with chapter 2 then? Okay, awesome. So the first question is, a 50-gram super ball traveling at 25 meters per second bounces off a brick wall and rebounds at 22 meters per second. A high-speed camera records this event. If the ball is in contact with the wall for 3.5 milliseconds, what is the magnitude of the average acceleration of the ball during this time interval? So the first thing that we want to do is write down all of our knowns. So it tells us the mass, which in this case may or may not be important, because from looking at it, we might be able to tell that it's a kinematic question, since it gives us initial final velocity and a time. So when it says 25 meters per second, we know that that's our initial velocity, because that's what it starts at. And then it says it rebounds at 22 meters per second. And what we want to remember with that is that when the ball is hitting the wall, it's going one direction, and when it's bouncing off, it's going a different direction. So our final velocity is going to be in the opposite direction of our initial velocity. Okay, and then it tells us our time, which is 3.5 milliseconds. And if we convert that into SI units, that would be 3.5 times 10 to the negative 3 seconds. And the kinematic equation that we might want to use here is based off of the variables that we have. So since we have 3 knowns and all of those fit into this formula, VF equals VI plus AT, then we can use that equation to calculate our acceleration. So when you plug in 22, oh sorry, this is supposed to be negative 22 because as I said, it bounces off the opposite direction. Negative 22 equals 25 plus a 3.5 times 10 to the negative 3. The acceleration that you end up getting is negative 13429 meters per second squared. Does anyone have any questions on that? Or anything about that concept? Okay, cool. So, we'll move on to chapter 3, and then we can come back if we have time. I only included one problem from chapter 3, but let me know if you have any other questions on it, because this chapter is mainly vectors, which we use in other places. But so the question is asking us what if we can find the displacement of all of these vectors combined, essentially. It says a novice golfer on the green takes 3 strokes to sink the ball, so 3 vectors. The successive displacements of the ball are 4 meters to the north, 2 meters northeast, and 1 meter at 30 degrees west of south. Starting at the same initial point, an expert golfer could make the hole in what single displacement? So we have 3 vectors that end up right here, and it's asking us what one vector could take us from the initial starting point to that same point. So what we're going to do is add our vectors and then see what the resultant vector is. So our first vector, it says that it goes 4 meters north, which north is up and down, so that would be the j direction, so 4j. The second vector is 2 meters northeast. And when it says northeast, what we assume that that's at a 45-degree angle, so exactly between north and east. So that gives us 2 cosine 45 for the I component, plus 2 sine 45 for the j component. And then for vector 3, it tells us that it's 30 degrees west of south. So you could either calculate that out and write out what your I and j components are, or you could just look from the x-axis. So since the x-axis is here and we know we're stopping here, that's going to give us 180 in this direction, plus another 60 in that direction. So it's 240 degrees from the regular x-axis. So if you put 240 degrees in your calculator, it should give you the correct answer. So that vector would be vector 3, and it's only 1 meter, so 1 meter cosine 240 I plus 1 meter sine 240 j. Does anyone have any questions on how we got vector 3? Yes? Okay, so really all that we did is we took what that angle would be from the x-axis. It told us it's 30 degrees, but that's not 30 degrees from the x-axis. It's on like the y-axis in kind of a weird position. So we just added up what it would be from like the positive x-axis, because that's what your calculator would calculate, right? And then we can just put it regularly into I and j components using sine and cosine. Another way that you could do it is find sine 30 and cosine 30, and then you would just have to realize that the sine would actually be the negative x value and the cosine would be the negative j value, because if you wrote this out as a triangle with this angle and you use sine, you would get this part, which is in the x direction, right? And you would get, for cosine, you would get a j value. Does that make sense? So either way is fine that you want to do it. Okay, so now that we have our 3 vectors, what we would do is add all of them up. So our resultant vector would be equal to vector 1 plus vector 2 plus vector 3. Okay, so what we can do is add all of our i's and all of our j's. So the I components would be 2 cosine 45 plus 1 cosine 240. That would be the I. And then the j would be 4 plus 2 sine 45 plus 1 sine, that's just the like distance value, 1 sine 240. And that would be the j. So in the end, when you add those values, what you should get is 0.914 I plus 4.548 j. And then if you calculate and get a different answer, just let me know. I might have made a calculation error, but yeah. Any questions on that? For the people who just got here, if you don't have this review, it's on the SARC website under Physics 1, or it's on the Study Union website under Physics 1 if you need it. Okay. Any questions on that at all? Or the concept of like adding vectors, subtracting vectors? Okay, cool. Bless you. So moving on to chapter 4. Okay, so this one says, to start an avalanche on a mountain slope, an artillery shell is fired with an initial velocity of 300 meters per second at a 55-degree angle above the horizontal, and it explodes on the mountainside 42 seconds after it is fired. So we want to know the x and y coordinates of where it explodes relative to its firing point. So what we have to do for that is calculate what, like separate it into x and y components. So we know our initial velocity, but we don't know our initial x and our initial y. So the way that we would calculate that is using sine and cosine. So the x component would be 300 times cosine 55, and the y component would be 300 times sine 55. So after that, we know our time, which is 42 seconds, right? And we know our acceleration in each direction. So in the x direction, generally for projectile motion, we would have an acceleration of 0 unless it tells us that we have an acceleration in the x direction. So acceleration in the x is 0. And generally for y, it's just going to be the acceleration of gravity. So from this information, we'll be able to use a distance equation to find the distance. So for x, the delta x is going to be equal to vix times time plus 1/2 axt squared. And since we have no acceleration, this component just crosses out. And we can use 300 cosine 55 times 42 seconds. And that's going to get us a distance equal to 7,227 meters. So that's the final x coordinate. And then our y coordinate is going to be calculated the same way with viy plus 1/2 ayt squared. Oh, sorry, viyt. And our viy is going to be 300 sine 55. Our time is 42 seconds. Our acceleration is negative 9.8. And then our time is still 42 seconds. So that value is going to be equal to 300. And then plus 0.5 times 1,678 meters relative to its firing point. Any questions on that? Or projectile motion or using these equations? Yes?
That's 7,220.
Yes, sorry. Okay. Are we good on this? Okay, so moving on to chapter 5. Okay, so this problem, what we would want to do first is it's already essentially drawn a free body diagram for us, but we will still have to write the equations ourselves. So the question asks, an object of mass m equals 1 kilogram is observed to have an acceleration a with a magnitude of 10 meters per second squared in a direction 60 degrees east of north. So it writes out for us what direction that is. And the force F2 acting on the object has a magnitude of 5 newtons, and it is directed north. So we want to determine the magnitude and direction of the other horizontal force. So we already know that this is equal to 5 newtons, and we know that this is equal to 10 meters per second squared. So the best way to begin is sort of like we did in the previous problem, which is to divide it into x and y components. So our acceleration in the x direction is going to be equal to 10 times either sine 60, which would give us this part, or cosine 30, which is going to use this angle to give the same component. They'll end up being the same thing. So let's say we use sine 60, and that value is going to be equal to 8.66 meters per second squared. So that's going to be our acceleration in the x direction. Any questions on that? Okay, so then when we're looking at all of the forces in the x direction, the only force that we have acting in the x direction is F1. F2 doesn't act in the x direction at all. So when we're looking at the forces, that's going to be equal to m times the acceleration of x, and the only force we have is F1. So since we know the mass is 1 kilogram, we can plug that in, as well as our 8.66. And then our F1 will be equal to 8.66 newtons. Any questions on that? Okay. So, moving on to chapter 6. We're going to look at a pendulum problem. It tells us to consider a conical pendulum with a mass of 80 kilograms. So the bottom part has a mass of 80 kilograms. It's on a string with a length of 10 meters, and it makes an angle of 5 degrees with the vertical. So we want to determine the horizontal and vertical components, as well as our radial acceleration. So the way to do that is to first draw out a Freebody diagram. So that's going to be our pendulum, and we know that tension is going to be acting because of the string. The other forces on the object are just going to be gravity acting down. And we'll also have a force that's caused by the centripetal acceleration, and that's going to act in the opposite direction of tension. So when we divide this into components for x and y, our forces in the x are only going to be based off of the x component of tension and our centripetal force. And since it's not moving left or right, then all of that is going to be equal to 0. As far as our y, it's going to be similar. So we're going to have our y component of tension and then our force of gravity. And both of those are also going to be equal to 0. So when we want to convert our tx into something that's a component of t, we know that our tx is going to be this part and our ty is going to be this part. And since we know that this angle is 5 degrees, then we know that tx is going to be the sine part because it's opposite to the angle. So tx equals t sine 5 degrees, and ty is equal to t cosine 5 degrees. Any questions on that? Yes? The centripetal acceleration points towards the center. The centripetal force always acts the opposite way. So it's counteracting that part. Any other questions? Yes? Yeah, that's FG. Sorry, it was kind of close, but. Okay, any other questions so far? Okay, awesome. So when we're going back to plug in components for these equations, first let's look at F in the y direction because we are pretty comfortable with determining the force of gravity probably at this point. So forces in the y are going to be equal to 0. And our ty, as we said, is t cosine of 5 degrees. And then our Fg is mass times gravity. So we know that our mass is 80 kilograms. That gravity is 9.8. So from there, we can calculate our the force of t. So that's 80 times 9.8 divided by cosine 5 degrees. And that gets us a force of 787 newtons. And when we're dividing that back into tx and ty, we can just do the same thing. So tx is going to be equal to that times sine of 5, which is 68.6. So tx equals 68.6 newtons, and ty is equal to 784 newtons. Now, when we're looking for the radial, or does anyone have any questions on that part first? We took this and plugged it in here and found tx and ty. And ty should also be the same as the force of gravity, right? Because they're balancing out. Yes?
Can you go back over like the
Okay, yeah, of course. So what we found here, we can see in our free body diagram that we only had 3 forces. This was a component of a force. So first we only had Fc acting in the x direction. The only other thing acting in the x direction is a component of tension. It's not all of tension, it's just a component of it.
Okay.
So we define that as Tx. And the way that we calculate that component is based on tension itself, but it's only the part that's on this side of the triangle. So we use trig to say that T times sine of this angle is going to be equal to that part. Just based on that sine of 5 degrees would be equal to opposite over hypotenuse. And our hypotenuse is tension, and our opposite is Tx. So when you rearrange that, you get T sine 5 degrees.
Could you use like the opposite of mass times gravity, like
No, it's okay. Go ahead if you have.
okay, so like the tension is obviously going to be opposite to whatever force is driving it the other way.
Right, right.
So could you use the force of gravity and like the sine or cosine?
Yeah, you could also use it. Sorry, this isn't very clear, but this is also the force of gravity. I'll rewrite it. So like the forces in the y are equal to tension in the y minus the force of gravity, and that's equal to 0. So
Okay.
both of these formulas we can use. In this case, we have enough information that we could use either one. In some cases, you would have to use both to cancel things out. Yes?
So how do you know if it's equal to 0? Like, how do you know it's stationary itself?
It actually is swinging, but it's not moving. It's moving in a circle. It's not moving into or out of the circle, and it's not moving up or down. So those forces themselves are equal to 0 in the x and y direction.
Oh, okay.
Does that make sense?
Yeah. Also, kind of going off of her question, is the reason why they're equal to 0 not only because they're not needed, but because they kind of cancel each other out?
Sorry, can you repeat that really quick? So they cancel. What cancels each other out?
Like, Ty and F and G, do they kind of cancel each other out?
Yeah, exactly. Yeah, they cancel each other out. Yeah, no problem. If they didn't, if the force of gravity was stronger than the tension, then it would be like falling down. If tension was stronger, it would be pulling it up, because there would be an acceleration. So when we set it equal to 0, what that means is there's 0 acceleration, because force is a combination of mass and acceleration, right? And there is a mass, but the acceleration is what causes it to be 0, because there's 0 acceleration. Does that make sense? Okay. So questions on the first part of this question? Okay, so then we're trying to find the radial acceleration, right? And the radial acceleration comes from the centripetal force, because radial acceleration is what causes the centripetal force. It's like how you were saying that centripetal acceleration goes towards the center. Well, radial acceleration acts the opposite direction, which is the same direction as this force is. So that's why they're referring to it as radial acceleration. Okay, so we want to find that acceleration itself. And the way we do that is that we now can find our Tx, right? And we found it to be 68.6. So when we say that 68.6 minus the force of the centripetal or radial force, whichever one you want to call it, is equal to 0, then we can determine that this is a combination of mass times centripetal acceleration or radial acceleration, whichever one you want to call it. And then we can divide out our mass from 68.6 to get our acceleration. So we just do 68.6 divided by that 80 kilograms. And we get that our centripetal or radial acceleration is equal to 0.8575 meters per second squared. So I tend to call it centripetal, but technically in this case it would be radial because it's going out, right? But the magnitude is more important than the direction, really. So I plugged in 68.6 over 80 is equal to the radial acceleration. Any questions on that? Okay. And then also I apologize, I didn't copy this entire question, so there's a component missing that actually asks you the question. So just ignore that for now. Okay. Chapter 7. Okay, so here's where we start talking about Hooke's law. So it says Hooke's law describes a certain light spring of unstretched length, 35 centimeters, so that's its equilibrium length. When one end is attached to the top of a door frame and a 7.5 kilogram object is hung from the other end, the length of the spring is 41.5 centimeters. So we want to find its spring constant. So the way that we're going to do that is to use our equation for Hooke's law, which is that force is equal to the spring constant times the x value. And our x value is going to be our distance away from equilibrium. So in this case, our distance away from equilibrium would be 41.5 minus 35 centimeters. And then when we have it in centimeters, what we're going to want to do is convert it into meters, since that's the SI unit, so we can divide by 100. And then our force is going to be equal to mass times acceleration. Since we're hanging it vertically, our acceleration is going to be the acceleration of gravity. So we have our mass, which is 7.5, or we have mass times acceleration. Our mass is 7.5, and our acceleration is 9.8. Yeah, it depends. Usually, they write it like this. You're right. Does that help answer your question? Okay, cool. Theoretically, when they talk about x, usually they're talking about when it's stretched a distance, it's a negative x. So that's what will cause the negatives to cancel out. So then these two would be reversed, which would cancel out the negative. Okay, so then we have 7.5 times 9.8 times 100. And then that divided by 41.5 minus 35. And that gives us a K value of K equals 1,130.8 newtons per meter squared. Okay. Or is it newtons? Yeah, newtons per meter squared, right? Or it might be newtons times meter squared. Sorry, I forgot the unit. But that's our K value. Any questions on that value, or how we use Hooke's law? Okay. So then for the second part of the question, it says that it's taken down, so we don't really have to worry about gravity anymore. And the force is caused by two people pulling on it, and they're each pulling with a force of 190 newtons. So that's going to cause our spring to stretch in both directions, but it's going to stretch equally in both directions, right? So we can just consider it one force together. And so our force 2 is going to be equal to 190 times 2. And then that force is still going to be equal to our kx. So F2 equals negative kx. And then so we have 380 equals negative k times, which we know is 130.8 times x. So when we do 380 divided by k, we get that x is equal to 0.336 meters, and that's going to give us 33.6 centimeters. Any questions on that? Yes?
I do have a question. What would happen, what would they have to give you in order for you to calculate the horizontal spring constant?
The spring constant is always the same.
But say
Oh,
it's a
I see.
different question, how would you calculate it with time?
You would either have to be given the force or determine the force. Like if they give you acceleration and a mass, you could determine the force, right?
Okay.
Because the force is mass times acceleration.
Okay.
So then you could find k. Does that answer your question?
Yes.
Okay, and then you had a question?
I believe it.
Sorry?
I believe it.
Oh, okay. Okay, cool. Okay, so are you good on this question? Okay, awesome. Moving on to chapter 8. Okay, let's do number 16 because I think that probably summarizes the chapter a little better than 15. And, okay. So this one is asking you, it's more theoretical, right? Let me see if I can zoom in. Okay, so a boy starts at rest and slides down a frictionless slide. Sorry, that is really bad quality. But it says the bottom is at a height like small h above the ground. So if he starts at like big H and ends at small h, and then he strikes the ground at a certain distance d that we don't know yet. So we're trying to determine the initial height in terms of other variables. So this is all theoretical. Okay. So the first thing that we might want to do, given that we have two height variables, is that we can set it up in terms of energy, like an energy balance equation, because that way we can easily use our height, and we'll also have to use velocity. But at the top of the slide, he doesn't have an initial velocity, so the only kind of energy that we have is potential. So usually when we start at a certain point, we're calling this point 1, we look at our total energy as our kinetic energy plus our potential energy. If we had a spring, we would have a different kind of energy, right? There's elastic potential and there's gravitational potential. But since we don't have a spring, we just have a height, it's going to be gravitational potential energy. So gravitational potential energy, and we don't have a kinetic energy because kinetic energy is based off of 1/2 mv squared, right? So you need a velocity to have kinetic. And you need a height to have potential. But in this case, we do have a height, so that's not a problem. So at point 1, all of his energy is in gravitational potential, which is equal to mg, and then the big height that we have, like capital H. So our second position is point 2, which is at the small h. And in this case, again, we're going to look at kinetic and potential. There's still no spring, so no elastic potential, but there is gravitational potential because he has some kind of height. And there is a kinetic energy because once he starts moving, he's going to have a velocity. So that's going to be 1/2 mv squared, and then mg little h. And since there's no energy loss to friction or anything else, then these two energies are going to be equal to each other because it's conserved. So mgh is equal to 1/2 mv squared plus mg small h. Okay, so our next step is that since this asks for everything in terms of h and d, we're not going to be able to use v. We're going to have to replace it with something. And we're also not going to be able to use m, but luckily all of those cancel out. So the way that we would be able to replace v is if we can replace it with d, right? Because the question asks to put it in terms of d as well. So in order to do this, we might want to use kinematics. And the most basic kinematic equation that we could use with this is talking about our velocity in our x direction and our distance that we're going to move, because we're moving in the x direction. So the way to do that is to say that our velocity in the x direction is equal to our distance over time. Since that's generally how we calculate velocity. So any questions on that part? Sorry. No? Okay. And then we don't have our time either. So that the way that we're going to want to do that is look into the y value. So we set everything up in terms of x. We don't have an acceleration in x, so it's not a problem. But we do have an acceleration in the y. And when we're looking at point h, it's telling us that point h is like flat. So at that point, it wouldn't have a vertical velocity. It would only have a horizontal velocity. So that will make it easier when we set things up in terms of y. So what we would want to do is look at our distance in terms of y, which is going to be like delta y, which could also be called small h, right? Because small h is going to be how long it takes him between the top and the ground. And since he's going down, we can call that, we can either call it positive or negative depending on how we're looking, but I'll call it negative since he's going down. Then that would be equal to v iy times t plus 1/2 ay t squared. And we know that we don't have an initial y velocity, but we do have a y acceleration, which is going to be equal to gravity. So negative h equals 1/2 negative g t squared. Okay, so what we're going to do now is define t so that we can bring it back up to this x equation and find vx, since this is also vx. And we can cross out the negatives, move over the 2. So we have 2h divided by g, and that's equal to t squared. When we get rid of the squared, we get the square root of this value. Okay, is everyone with me so far? I know it's a lot of kinematics. Yeah, okay. So then when we want to go back to Vx, what we do is we plug in this entire value to here. And then we can see that Vx is equal to d over the square root of 2h over g. Okay. Now, we have Vx. We want to plug it back into here. And so what we do is we say that gh is equal to 1/2 d over the square root of 2h over g squared plus gh. Okay, then when we square this, we get d squared over 2h over g. And we want to move this up to the top. So what that will give us is gh equals 1/2 g d squared times 1 over 2 little h plus gh. Okay, and then the next thing that we can do is cross out all of the g's and multiply, so we move everything over, and what we should get is h is equal to d squared times 1 over 4h plus 8, little h. Okay, any questions on that? So after you get down the energy balance and the kinematics, it's just algebra and moving things around. Is everyone with me on that, though? Okay, awesome. So moving on to chapter 9. Okay. 3 carts of masses m1 equals 4 kilograms, m2 equals 10 kilograms, and m3 equals 3 kilograms move on a frictionless horizontal track with different speeds of 5 meters per second to the right, 3 meters per second to the right, and 4 meters per second to the left. And it says Velcro couplers make them stick together after they collide. So we want to find the final velocity of all of them, which is going to be the same because they collided, right? So this is going to show us that momentum is conserved. So the formula we use for conservation of momentum, in this case, since we have 3 objects, is going to be m1 v1 plus m2 v2 plus m3 v3. And all that is going to be equal to the combined mass of all of them. So m1 plus m2 plus m3 times vf, since they all have the same final velocity. So from there, we know that since it's just asking us for the final velocity, it's just vf equals m1 v1 plus m2 v2 plus m3 v3 over all of their masses combined. And so the main thing to remember here is when you're plugging it in that one of them is moving to the left, so you have to make it negative. So m1 is 4 times its velocity 5 plus 10 times its velocity of 3 plus 3 times its negative velocity of 4, and all that over 4 plus 10 plus 3. And so that value is going to be equal to 2.24. 2.24 meters per second. And since we defined our positive direction as going to the right, it's going to be 2.24 meters per second to the right. Any questions on that? If you can see that. Okay. And then when it says that, it asks if your answer changes if they all stick together, like if it matters if they all stick together at the same moment or if they stick together in a different order. And the answer would be no, it doesn't matter, because momentum is conserved regardless of like when they collide. So if your initial position is all of them moving and your final is all of them sticking together, it doesn't matter what happens in between. Okay? Any questions on that? Okay. So for chapter 10, yeah, I guess we can. So this one is pretty straightforward. It's like kinematics, but in the angular direction. So what you would do is our angular position is just like a regular x position. So when you're plugging in your time, you would just plug in 0 for the time. So like for A, you would just plug in 0. So the angular position equals 5 plus 0 plus 0. So it would just be 5 radians. Because it's asking you to determine the angular position at 0 seconds. And then if you want to find your equation for your angular velocity, you would just have to derive that equation. So when you derive it with respect to time, then we don't have a 5 anymore. And we have 10 plus 4t. And then when you plug in 0 again, our angular speed at that time would be 10. Or when we plug in 0 for time, sorry. Then our angular acceleration would be deriving the angular velocity equation, so we would just have 4. So it would be 4 no matter what. So this is 4 radians per second, and this is radians per second squared. For part B, we do the same thing, but with plugging in 3. So our angular position would be 5 plus 10 times 3 plus 2 times 3 squared, which is equal to 5 plus 30 plus 18, which is 53 radians. And our omega would be 10 plus 4 times 3, so 22 radians per second. And our angular acceleration would still just be 4, because we don't have any place where we can plug in time, so it's just 4 radians per second squared. Any questions on that?
Is angular speed and angular velocity the same thing?
They are. It's similar to when we talked about regular speed and regular velocity, right? So velocity, the direction does matter. Speed, it's just the magnitude of velocity.
Okay, so, yeah.
Yes.
For these types of problems, is acceleration usually going to be constant?
I mean,
Right, because for kinematics, we can only use
yeah. Usually for kinematics, it is constant. Like occasionally you'll see one where they want you to do some like calculus or something and it's changing, right? But like usually it's constant. Any other questions? Okay. Do you guys want to do another one on 10 since that wasn't very like in depth, or just keep going? Okay, we'll do chapter 11 then. So, chapter 11, starting on question 26, we have the position vector of a particle of mass 2 kilograms as a function of time is given by r equals 6i plus 5tj, where r is in meters and t is in seconds. So we want to determine the angular momentum of the particle about the origin as a function of time. So it sounds a little bit more complicated than it really is, because the way that we calculate angular momentum is r cross regular momentum, right? And another way to write that is like we just take out the mass, so mass times r cross v, because this is m cross v, right? Or, sorry, not m cross v, but m times v. Does that make sense? Linear momentum is m times v. Angular momentum, we do r cross linear momentum. Okay, so we know our mass already, which is 2 kilograms. And then we know our vector for r, which is 6i plus 5tj. And then our velocity is given to us in terms of, where does it say it? Oh, okay. So we don't have our velocity, but we can determine our velocity, right? So we need velocity as a vector, and we only have it in terms of position. So the derivative of r is going to be equal to velocity. And so when we derive this value, we get nothing for I and only 5 for j. So it's just 5j. Does that make sense? Okay, so then when we go back to our L, we have 2 times 6I plus 5tj cross 5j. And when we do a cross product, you can't cross two vectors that have the same direction because you're looking for a component that's perpendicular, or you're looking for two things that are perpendicular to each other, right? So since j and j are in the same direction, when you cross them, it's just going to be 0. So the only thing that matters here is the I cross j, which is 6 cross 5. And then that's going to be in the direction of the third vector, like direction, which is going to be k. Does that make sense? So it would just be 2 times 30k, which would be 60 kilograms times meters squared per second. Does that make sense as far as the cross product, or do you want to go through it a different way too? Because another way that you guys might have done cross product is like with the lines and everything, and you just go, like, because that would also work, it would just take longer. It's a little bit easier if you recognize that I cross j is what you want. You don't want j cross j because that doesn't make sense. That's like not going to be anything. So does that part make sense? Yeah. Yeah. So this is the derivative of r. Sorry, who asked that? Okay, yeah, sorry. Yeah, so it's the derivative of r. So when you derive 6I plus 5t in terms of t, then the I part would disappear, right? Because there's no variable there. So it would just be 5j. Okay,
why do you take the derivative?
Because velocity is the derivative of distance.
Okay.
Okay. Is that one okay then? All right. So, okay. So chapter 12, I know some people said they didn't go over chapter 12, but we'll just do like one problem on it then. The first, I mean, we could also do, the center of gravity is very similar to the center of mass problems, so we'll go with this problem, number 30. Sorry. Let me find that. Okay, so this problem is a pulley. So we're going to be dealing with both forces and torque here. So it says find the mass of the counterweight needed to balance a truck with mass m equals 1,500 kilograms on an incline of 45 degrees. So both pulleys are massless and frictionless. So the way we would begin is looking at the forces in this direction, right? So we know that since we're balancing it, our net movement is going to be 0, and there's not going to be any acceleration. So our total forces would be 0. But we do have forces acting on this truck, right? So if this was the truck, the two things that would be acting on it would be gravity going this way, but only a component of gravity, and then 2 tension forces going that way, right? Because there's 2 ropes attached to it, and they would be balancing each other as well. So what we would want to do here is find the component of gravity that we need, and since we know our angle right here is 45 degrees, then our component that's going to be going this way is only going to, our gravity usually goes here, right? But we want the part that's going like this. And so the way that we would find that is, in this case, it doesn't really matter if you use sine or cosine, but the correct one to use would be sine, which you guys are probably familiar with. So it would just be mg sine angle is going that way, and then it's balanced out by our 2 tension forces. Any questions on that? Or why we use sine 45 instead of cosine? Okay, yes? The force of gravity is pulling down on the truck, but it's not pulling down, like since it's at an angle, we're only using the component that's going that way, right? Like at an angle as well. Okay. Okay, so we can plug in what we know for that, which is 1500 times 9.8 times sine 45 minus 2t, and that's equal to 0. So what we end up getting is that it's 0.5 times 15. And our tension force should be equal to 5,197 newtons. Any questions on that? So so what we're asked is the counterweight mass. Right now we only have the tension, but we do need that in order to find the mass of the counterweight because we're going to have to look at torque next, and torque is based off of those those forces that are pulling in each direction. And the tension force is the one that's pulling on the pulley in that direction. So when we look at our torque balance, what we have is that torque is also going to be equal to 0 because we don't want it rotating, right? It says that it's balanced. So if torque is equal to 0, we look at the two forces that are pulling on it. So the tension force is going this way. Sorry. And then the mass, the force from this mass, is going this way. So they're going in opposite directions, right? One is trying to rotate it clockwise, one is trying to rotate it counterclockwise. And the way that we calculate torque is the force from the center times the radius it is from that center, right? So that torque is going to be equal to our tension going this way times the smaller r because it's attached closer to the center minus, since they're going in opposite direction, that mass that's pulling on it. And the force of that mass is going to be based off of gravitational force, right? So it's that mass times gravity. And then that force itself is 3r from the center. If you can see from the picture, it's attached farther. So there's small r and then there's 3r. And all that's still equal to 0. So when we calculate out what that mass needs to be, we would say that 3 mg is equal to tension. So the mass is going to be equal to T over 3 times gravity. And then the answer that you would get for that is that the mass is equal to 177 kilograms. Okay, any questions on that? Or any questions on torque in general? Or how we calculate torque? Yeah, so torque, there's actually another problem in here that is a better demonstration of torque, I think. But what it is that torque is what's causing it to try to rotate. And so we calculate that by the force that's pulling on a moving object, or a circular object, by the distance it is from the center. So in this case, what we did was we used, depending on which one it was, this one was, we only used r because it was r from the center. It was inside the smaller circle. And this one we used 3r because it was farther. It doesn't matter which direction it's pointed in. It just matters which way it's pulling on it. So even though this is at an angle and this is straight down, that doesn't matter because it's a circular object. One is pulling it clockwise and one is pulling it counterclockwise. Yeah?
Is the reason why you can't just set each fork of the ropes equal to each other because that they're attached at different lengths?
So, yes, I think so. You're saying the forces themselves?
Right.
Yeah, yeah.
If they were attached at the same R, you'd be able to set the torque of the truck rope equal.
The tension?
Yes.
Yeah, the tension equal to the gravitational force. Yeah, exactly.
Okay.
If they were the same distance.
Okay.
But in this case, they're a different distance, so you have to take that into account. Did that answer everyone's question on what torque is, or any other questions? Yeah? Because this part of the rope isn't attached to the circle, only one of the ropes is. So only the tension of one of them is pulling on it instead of both. But then later there's both two of them, so like down farther. Any other questions on this? Okay. Okay, so the one from chapter 13 that I put on here, it's not really, it's probably even more than you guys would do because it's not really related to what questions I've been asked before. How many of you have chapter 13 on your test? Most of you? Okay. Because I know some professors skip it. Yeah, so if there's another question, I don't think this one is a good use of time, so if you want, I'll upload a different question with a solution other than the one I put on here, because this one isn't a good example of what you guys have been having in class. Yeah?
Are the solutions going to be posted?
Yeah, the solutions will be posted in the same place that this review is posted. Either go on the START website and go to Physics 1 under my name, or you can go to the Study Union website under Physics 1. So they're both WordPress sites. So if you type like Study Union WordPress or SARC WordPress, check them out. Any other questions about that? Okay, so moving on. So chapter 15 is the last one I put on this. Do any of you guys go past chapter 15? No? Okay, that's good. You do? Oh, okay. You do? Oh, okay, right. Okay, so I don't have any questions on here, but I can try to find a good one and also put them online if you want. Okay, so chapter 15, 32. Okay, so essentially this one is, the question is saying a physical pendulum in the form of a planar object moves in simple harmonic motion with a frequency of 0.45 hertz. It has a mass of 2.2 kilograms, and the pivot is located 0.35 meters from the center of mass. So it's asking you to find the moment of inertia. So this might not be a formula that you guys are super familiar with, but there is a formula that says T equals 2 pi square root of I over mgl. And from that point, essentially what you would have to do is plug in, because we have G, which is 9.8. M is 2.2 kilograms, and then the L is the 0.35 that it gives us. It gives us frequency rather than T, so we have to convert that. So frequency equals 1 over T. So 0.45 equals 1 over T. And then when you do 1 divided by 0.45, you get that T is equal to 2.22. So that's the period. And you say 2.22 equals 2 pi root I over 2 times 9.8 times 0.35. And divide that out. And then the answer I get for that is that the moment of inertia is equal to 0.86. And that's, I believe, kilograms times meters squared per second. I might be wrong about the unit, but because it's, yeah. But any questions on that? So the main thing about chapter 15, if you guys do have it on your test, is that you need to know how to use the formulas. So use everything that's available to you, and even if you might have to rearrange some of them. Hopefully your professor gives you a formula sheet. If not, just try to remember as many as you can. Any questions on that? Yes?
Is that thing in the square root, is that kind of like omega?
I mean, yeah, because when we calculate moment of inertia, how do we calculate it usually? It's like mr squared or like some form of that, right? So when we divide by m and we divide by an L, it's kind of like, it's a different unit. It kind of like is a distant, like a time unit, I believe. I'm not exactly sure where it comes from. I think that if you used all of your equations from this chapter and tried to rearrange them, you would eventually get this. But it's a lot of, yeah, reformatting those. Any other questions on that? Okay. So we're going to take a 5 to 10 minute break, just like if you want to go to the bathroom, get water, anything, and then come back. If you have any other questions when you come back, just let me know. Okay. Okay, we're going to get started again. Okay, we've pretty much done one question from every chapter. So if you guys want, we can just go back to the beginning and start doing one from each chapter again. Is that good with everyone? Okay, cool. So going back to chapter 2, this question says a particle moves along the x-axis. Its position is given by the equation x equals 2 plus 3t minus 4t squared with x in meters and t in seconds. So determine its position when it changes direction and its velocity when it returns to the position it had at t equals 0. So this is kind of similar to something you might see in calculus, and it wants to make sure that you know the relationship between distance and velocity. So when the direction changes is going to be when the velocity is equal to 0, right? So we're going to want to find the velocity equation, which is the derivative of the x equation. So if we do d dt of x equals 2 plus 3t minus 4t squared, then what we get is v is equal to 3 minus 8t. So when v is equal to 0 is when it's going to change direction. So 0 equals 3 minus 8t, and that's going to end up giving us t equals 3/8 of a second. Okay, any questions on that? So the second part is asking us for its velocity when it returns to the position it had at t equals 0. So the first step would be to find what the position originally is when t is equal to 0. So what we're going to do is say that x is equal to, so this is part A, b, x is equal to 2 plus 3, 0 minus 4, 0 squared, which is equal to 2 meters. So we know that we want to know what the position, or what the velocity is when it returns to a position of 0. So we want to find another time other than 0 when the position is 2 meters. So we'll set x equal to 2, and then use our equation to find 3t minus 4t squared. So when you subtract 2 from both sides, you get that 0 is equal to t 3 minus 4t. So one of the solutions is 0, which makes sense, because that's the position we had at 0. And then the other t value would be equal to t equals negative 3 over negative 4, so 3/4 of a second. So that tells us at what time it's going to be at that position. Now we have to find the velocity for that time, which again, we're going to use this equation. So v equals 3 minus 8 times 3/4, which ends up giving us negative 3 meters per second. Sorry if that's running off, but does that make sense to everyone? Any questions? Okay, cool. So, moving on to the next chapter. I only had one problem from chapter 3, so moving on to chapter 4. Problem number 6. Okay, so this one is kind of long, but like to read. But really, it's just asking us for a change in x and a change in y. So it says an aging coyote cannot run fast enough to catch a roadrunner. So we have two objects moving, right? And the coyote has roller skates that have an acceleration of 15 meters per second squared, and he starts 70 meters away from the edge of the cliff. So we want to determine the constant speed that the roadrunner has to have to get to the edge before the coyote. And so we'll start with that part. So we want first we want the speed of the roadrunner. And the way that we're going to do that is to find our distance, and so we have our distance, our acceleration. We want to know how much time it's going to take the coyote to get to the edge to know how fast the roadrunner has to go. So our distance in the x direction is equal to 70. Our acceleration is equal to 15 meters per second squared. And then our initial velocity is going to be equal to 0. So looking at just the x direction, we can use this equation, delta x equals vixt plus 1/2 at squared. So that's going to tell us that 70 is equal to, this part is 0, so 1/2 15 t squared. Okay, so our time is going to be 3.06 seconds for the coyote to get to the edge, so that's going to be the same amount of time that the roadrunner needs to get to the edge. So his velocity is going to, he's already running, so he doesn't have an acceleration, he just has a constant velocity. And he has 3.0 seconds to get there, and he's moving a distance of 70. So this was for the coyote. Okay, then for the roadrunner, we still have a distance of 70 and a time of 3.06 seconds, but our acceleration is 0. So we can use the same formula, really. It's going to be like delta x equals vixt plus 1/2 at squared, except this time this part will be 0. So we know that our 70 is going to be equal to his velocity times 3.06. And the velocity that we get for that is about 23 meters per second. Any questions on that? So we found how long the coyote takes to get there. Then we knew that the roadrunner had to have a velocity that gets him there in that amount of time or less. Okay, so the second part of the question is asking us it tells us at the edge of the cliff, the roadrunner escapes by making a sudden turn, but the coyote continues straight ahead, so he's going to fly off the cliff, and his skates continue to accelerate him. So he still has the acceleration in the x direction, that's 15, and also the acceleration of gravity is going to be acting on him as well. And we know that he's 100 meters above the floor. So it's asking how far he's from the base of the vertical cliff he's landing, so it's asking how far he's landing in the x direction. So what we know is that he's going to fall 100 meters and that he's going to go forward during that time. We just don't know how long it's going to take him to fall yet. So what we're going to do is say that, of course, in our x direction, we're still going to have acceleration that it tells us, which is 15I. So we know that our delta x is going to be equal to vix plus, or t plus 1/2 axt squared. And we know our acceleration. We don't know our time or our vix. So the way that we would find vix is to know that he's running at first and he's accelerating. He starts at 0. So his acceleration during that time was still 15. So his vix is going to be equal to his acceleration times the amount of time he was running to the edge, which we already found, right? It was the 3.06. So 15 times 3.06, his initial velocity is going to be 45.9 meters per second. And we can plug that back into here once we find time. We still don't have time, though. And usually when you have an x and a y direction and you're not able to find time for the x, you can use the y, because we know our y distance, right? So do you have a question?
I'm confused because it says the coyote starts at rest at 70 starts at rest.
Yeah, so what happened was he started at rest and then he accelerated over that 70. So we're talking about the initial velocity after he moves that 70.
Okay.
Does that make sense?
Yes.
So another way, if we wanted to write this out,
Okay.
I'll write it on the back, I guess, if there's not enough space. But he had VF is what we're considering to be our VI, when he jumps off the cliff.
Right.
But that's equal to his VI, which was 0, plus AT. So that's where we're getting the AT from. Does that make sense?
Yes.
Okay. So once we found that, we still need to find our like distance that he's going, or like, sorry, the time that he's going. What number was that? Number 6. Right, so we still need to find the amount of time that he's going, and the best way to do that is to look in our y direction. So our y direction, we know we can use the same formula, which is delta y equals VIYT plus 1/2 AYT squared. And we know in the y direction, since they were running along the top of the cliff, there was no initial velocity, right? But there is the acceleration of gravity, and he is going to fall 100 meters. So from that, we can get that negative 100 is equal to 1/2 negative 9.8 t, and we can call this t2, so t2 squared. So the first t was the time it took them to run across. This t2 is how long it's taking him to fall. Okay, so our t value should be about 4.5 seconds. So that's for t2. And this also is going to be t2. Any questions on that? Okay, so our delta x, we're going to plug in that 45.9, our 4.5, and then our 15 here, and again our 4.5 here. I know it's kind of crowded, but when you calculate that out, times, what I got was about 359 meters, so the delta x would be 359 meters. So that's how far he's going to go in the x direction. Any questions on that? Or any questions about how we switch between like the x and the y or anything like that? Okay, cool. So, oh yeah, and we also are asked the components of his impact velocity. So I'm going to write that on the back of this. So impact velocity is going to be his final velocity in both directions, right? So the x and the y. So when we're looking at, we had 3 different like velocities, right? We had the velocity when they began running, when he got to the edge of the cliff, and now when he's falling like to the bottom. So you can define it however you want, just like make sure you keep them straight so it doesn't get confusing, because I know like it can get confusing. But in this case, we're going to call them VXF and VYF. So VXF, so this will be the impact when he gets to the bottom. VXF is going to be equal to VXI plus AXT2, so the time where he's falling. And then VYF will be the same thing in the y direction. So. And we already found that our like VYI was 0. And we just found that our VXI was 45, I believe, or 45.9. So that was when he got to the edge. Our acceleration is still 15, and our T2 was 4.5. So his final x was going to be 45.9 plus 15 times 4.5. And that's an x velocity of 113.4 meters per second. Meters per second. Any questions on that? It doesn't go over far enough. Okay. But any questions on that part? Okay, and then our VYF was just going to be 0 plus our negative 9.8 times 4.5. And that's going to be a velocity of negative 44.1 meters per second. if it asks us his total final velocity, what we would do is take the square root of both the x and y components squared, and that would be like without it like his either direction necessarily, it would just be his total velocity. Does that make sense? Any questions on this problem? Okay. So moving on. Yeah, from chapter 5, the other problem was using relative velocity, so it's a little bit more complicated than what you would typically see from chapter 5. So we'll just skip over that one for now. We can come back to it if we have time, just because it's a fairly long problem. And yeah, so from chapter 7, I think we have 2 more. So like, which one from chapter 7 do you guys want to go over, 13 or 14? 14? Okay. Anyone else have a 14? Okay. Okay. Cool. Okay. So the basic principle of this is, okay, so an inclined plane of angle 20 degrees has a spring of force constant K equals 500 newtons per meter. It's fastened securely at the bottom so that the spring is parallel to the surface. We know the mass of the block, and we know the distance it is from the spring. So from this position, the block is projected downwards towards the spring with a speed of 0.75 meters per second. By what distance is the spring compressed when the block momentarily comes to rest? So the best way that I would think we could do this one is using an energy balance, because it's going to start with a certain energy and it's going to end with a certain energy because of the spring, right? Okay, so in the first place, like when it starts at the top, it's going to have both potential energy and kinetic energy, right? Because it starts with a speed and it starts with a height off the ground. And since like we don't know how far technically it is off the ground exactly, we just know that it's going to be farther than it is when it's compressed, right? So the distance that it is like d plus the amount that it's going to be compressed, right, which is x. So if we took this point to be 0, because when we're talking about potential energy, we can define any point to be 0. So if we take its finishing point as 0, then its initial point is going to be like the height, but it's going to be like based off of this, like, or like this as the hypotenuse, the x plus d. So what we want to do is find the height based off of d plus x. Does that make sense? Okay. So if we drew a triangle with like d plus x on the hypotenuse, and we had this angle, and we wanted to find the height, the way we would find it is by saying that like sine of the angle is equal to that height over d plus x. So our height is going to be equal to d plus x sine of the angle. Sorry if you can't see that, but does that make sense? Any questions? Okay. So when we're talking about our potential energy, like potential energy 1, it's going to be equal to the mass times g times d plus x sine of the angle. Okay, and our kinetic energy at that point is just going to be 1/2 mv squared. Okay, now when it gets to the bottom, it tells us in the question that it momentarily comes to rest at the bottom, right? So that means we don't have kinetic energy at the bottom. Also, we decided that that was going to be our height of 0, so it doesn't have potential energy at the bottom either. All that we have is elastic potential energy, since it's like compressing a spring, right? So our elastic potential energy is going to be equal to 1/2 kx squared. Okay? And that's elastic potential energy too. So the next thing that we can do is form an equation using an energy balance, since we shouldn't be losing energy during this process. So we know that mg d plus x sine theta plus 1/2 mv squared is going to end up being equal to 1/2 kx squared. And so we can plug in what we know, and we know that our mass is 2.5, gravity is always 9.8. Our distance is given to us as 0.3, and then we have x, 920, plus 1/2, 2.5. Our v was told to be like 7.75 squared, and then that's going to be equal to 1/2 times 500 times x squared. Any questions on that part? Okay, so we need to simplify everything down, and we're going to do that by multiplying out like the first part. So we're going to take out like the component that's used for x and the component that's used for 0.3. So what we would do first is 2.5 times 9.8 times 0.3 sine 20 plus 2.5 times 9.8 times sine 20 times x plus all of this is going to be on the left side of the equation. So when we say that 2.5 times 9.8 times sine 20, that's going to be 8.38. So 8.38 times x. And then when we multiply by 0.3 instead of x, we get that it's 2.5. For this part, we have 0.5 times 2.5 times 0.75 squared, and that's 0.7. And all of that's going to be equal to 250x squared. Okay, any questions so far? Okay, so this is going to end up being a quadratic formula, so it's 250x squared minus 8.38x minus 3.2. And when you end up solving it, I think, let's see, you have 8.38 plus minus root here. 8. So b squared minus 4ac, which is 4 times 3.2 times 250. And then all of that, so you essentially have 8.38 plus minus 57, and if you want it to be positive, it has to be plus. And then over 2a, which is 500. So the x value I got was 0.13 meters, which is equal to 13 centimeters. If someone else got something different, just let me know. Okay, any questions on that? Yes?
So how do you know what your x is going to be, whether you should add or subtract?
For this particular one,
Yeah.
I just did it as positive because otherwise it would be a negative value.
Okay. And that would just represent it.
Yeah, because it's going to be like, it's not going to be negative because it's not like stretching, it's compressing.
Okay.
Right? Yeah. Does that make sense? Any other questions? Okay, cool. So, moving on to chapter 8. Okay, number 17. So for this one, it's asking us to draw, okay, it says a 5-kilogram block is placed on top of a 10-kilogram block, and we're applying a force to the bottom one, and the other one is tied to the wall. So there's friction on each of them, and all of it, like the kinetic friction, is going to be 0.2. So first it wants us to draw a free body diagram and then determine the tension force. Okay, so the free body diagram for the top one is going to be easier because there's less forces on it, and it's going to look like this. We're going to have the tension force pulling that way, And then as always, there's the weight of the object and the normal force counteracting that. But because there's tension acting that way and there's a block sliding under it, there's going to be a force of friction sliding that way as well. As well. So friction is going this way. Friction of like A against B. And then our force on our other block is going to be some of the same forces, so it's still going to have a weight, but this time that's going to be the weight of A plus B, because of course A is on top of it, right? But the normal force acting up is only going to be the normal force of B, like called the normal force of B, and there's a force pulling on it that way, as well as the friction of itself against A, and the friction of itself against the ground. Any questions on that? Yes?
Why is the normal force on the black block just the normal force?
It's defined as the normal force of B, but like it's dependent on the weights of both. Like, does that make sense, kind of? Okay, because like it's just like A and B aren't combined, but so there has to be a force acting up, but it's like, yeah. Does that answer your question or no? Okay. It might make more sense if we, yeah, keep going. But okay, so because it's going to be balanced out by this force. So when we're looking at the first part of the question, which says, determine the tension in the string. So the tension is just going to be based on block A, right? Because the tension is going to be counteracting the friction, because block A isn't moving. Only block B is moving. So if we look at the friction or the forces in the X for block A, all that we're going to have is the frictional force minus the tension force, and that's going to be equal to 0. So all that we really need to find is the frictional force. And the friction is based off of the normal force times the coefficient of friction. And the normal force of A is going to be counteracted by the weight of A. So similarly, like the forces in the Y would be equal to 0, and it would be the weight minus the normal force. So we can calculate the weight, which is equal to the normal force, just by mass times gravity. So this is equal to 5 times 9.8 times 0.2. And that will give us a tension of 9.81 newtons. Or a frictional force of 9.81 newtons, sorry. But that is equal to tension. Any questions on that? Okay, so when we look at part B, what we're going to have to consider is that there's a lot more forces on it, but it's going to be set up similarly, right? So the forces in the X are going to be equal to like this force pulling it right minus the friction of A minus the friction of B. And since it is moving or accelerating to the right, then we will have an acceleration. So all of that's going to be equal to the mass of B times the acceleration of B. But in the y direction, it is not moving. So it's going to be a similar circumstance where the weight of A plus B minus the normal force of B is going to be equal to 0. Does that make sense? Or kind of answer your question more? Like when we set up the force in the y, it's going to look like this.
Right.
So when we solve for the normal force at B, it's going to be equal to 10 plus 15 times, or 10 plus 5, sorry, times gravity. So it's just 15 times 9.8, which is equal to 147. Does that make sense? Okay. Then when we're going back to solve for like f of x, so we have like, we know that our force, it tells us up here, the horizontal force is 45 newtons. So we know that 45 minus that frictional force, which we already found to be 9.81, minus the friction at B, which is mu times the normal force, right? That's all equal to the mass of B times the acceleration of B. And then when we plug in our last few things, which is 45 minus 9.81 minus 0.2 times 147 over the mass of B, which is 10, that's our acceleration. And our acceleration should be 0.576 meters per second squared. Any questions on that? Pretty good? Okay, cool. So, okay. Okay, let's do the sheet of metal one in chapter 9. So like center of mass. And it's not really clear to see here, but there's 6 little squares. So 1, 2, 3, 4, 5, 6. And it's asking us to find the x and the y coordinates of the center of mass. So if you guys remember, like the way that we usually calculate center of mass is the sum of all of the masses times their x coordinates over the sum of all the masses. So there's a couple ways you could do this. One is to divide like the object itself into different sections. I mean, you're dividing into sections either way, but you could either divide it into 6 individual sections, 3 sections, however many is easiest for you. In this case, we'll just do 6 because I think that might be a little bit easier. So we'll find the center of mass of each of the 6 little boxes and then add those and divide by the total mass. So what we do for that is we say that, like for object 1, its center of mass in the x direction is going to be right here, right? So that's going to be at 25. So 25 times its mass, which is 1m, is going to be on top. Then for object number 2, its center is at 15. So we have 15 times m. For 3, it's going to be at 5, so we have 5 times m. And it's going to be 5 for also 4 and 5 because they're at the same x distance. So 5m plus 5m. And then when we get to 6, it's also going to be 15. The total mass is going to be 6m because there's 6 objects with equal mass. Is there any questions on that? That's just for the x coordinates, not the y. So what we would end up getting is that we have all right, so it ends up being like 11.67 centimeters once you add all of these up and then cross out all the m's because the m's cancel out. So the x value is that. Any questions on that? Okay, so we're going to do y in the exact same way, but we're going to look at their y centers instead of their x centers. So y center of mass is going to be equal to, the center of mass for these 3 is all going to be 5 because that's their center up. So 5m plus 5m plus 5m. The center for this one will be 15. And then it'll be 2 like 25s. Sorry, that's a little messy. And then all of that will again be over 6m. And when you add those all up and divide by 6, what you should get is 13.33. Any questions on that? Okay, cool. So moving on to chapter 10 again. Number 23. So number 23 says a rotating wheel requires 3 seconds to rotate through 37 revolutions. Its angular speed at the end of the 3-second interval is 98 radians per second. What is the constant angular acceleration of the wheel? So we're given already that our distance is 27 revolutions. And the first thing that we want to do is convert that into radians. So to convert it into radians, all we have to do is multiply by 2 pi, which will give us 232. Sorry? Oh, 37, my bad. Sorry, I wrote in pen. Okay, 37 times 2 pi, which will give us 232. Yeah, I wrote that. So 232.5 radians. Okay, so we're trying to find the constant angular acceleration, so we're going to want to use a formula that will give us that. And the most simple one is probably similar to one that we use in kinematics, which is, the position is equal to omega I times t plus 1/2 alpha t squared, right? Since we're given omega I as well, which is 98, so we know that the 232.5 is equal to 98 times 3 plus 1/2 alpha times 3 squared. And the alpha value that we should get for that is 13.67 radians per second squared. Any questions on that? Okay, cool. So moving on to, we only have time for like a few more really, but do you guys have any in particular you want to go over? Okay, then we'll just keep going regularly. So number 28 tells us that a student is sitting on a rotating stool, and first he's holding dumbbells out, and then he's pulling them in. So that's his angular momentum is going to be conserved, right? But his speed is going to change because angular momentum is calculated by the moment of inertia I times our angular velocity. So when he's pulling it in, what he's doing is he's changing his moment of inertia, right? So in the first place, his moment of inertia is going to be the inertia of himself, which it tells us is 3, plus the moment of inertia caused by the dumbbells. So when we have an object going around another object, the way that we calculate that moment of inertia is by mr squared, as opposed to like the different equations that we have for like individual objects, like a rod. You might use like 1/6 or 1/12. Like it depends on the shape, right? But it doesn't depend on the shape when it's like you're holding it out from the center. Does that make sense? So for him himself, it already told us that it's 3. But for the two objects, we're going to use mr squared. So we have 2, because there's 2 of them, times their mass, times their radius, which in the first place is 1 meter. So 1 squared. And the value we get for that is just 3 plus 6, which is 9 kilograms times meters squared. And it tells us that our initial angular speed is 0.75 radians per second. So since we're trying to find omega f, the next thing we have to do is find moment of inertia final. So we're going to calculate it similarly because his moment of inertia isn't changing. He's still in the middle, so it's still 3. And there's still 2 dumbbells, and they're the same mass. The only thing that's changing is their radius. So instead of 1, we're going to square 0.3. And the value that we get for that is 3.54. So his final moment of inertia is 3.54 kilograms times meters squared. when we plug all that in at the end, we get that 9 times 0.75 equals 3.54 times omega f. So 9.75 divided by our inertia tells us that omega f is equal to 1.9 radians per second. Any questions on that? Okay. So moving on to chapter 15. Number 33 says a simple pendulum makes 120 complete oscillations in 3 minutes. And it tells us our gravity is 9.8 meters per second squared. So we're trying to find the period of the pendulum and its length. So, also, if you guys are leaving, could you please do the surveys before you leave? Thank you. Yeah, so it makes 120 complete oscillations, and it gives us our time. So the first thing we would want to do is convert our time into seconds. So 3 minutes times 60 seconds per minute equals 180 seconds. Okay, and then our time period, we typically calculate by how much time it takes to make an oscillation, right? So the way we want to do that is say that our time is equal to 180 seconds over 120 oscillations, because it takes us that long to make that many oscillations. So how much time does it take us to make one? And we find that it's 1.5 seconds. So that answers part A. Looking at part B, this is probably a more familiar formula for you guys. It's T equals 2 pi, the square root of L over G. Have you guys seen that? No? Okay. Well, have you seen just T equals, you haven't seen anything with L over G? Or the acceleration?
Is that equal to omega?
I don't think it's equal to omega, no.
Alright.
Sorry?
Yeah, 1 over omega?
1 over omega. Yeah, actually, I think so, you're right. Because it's distance and acceleration. Yeah. Yeah, that is. So this is the one you would want to use in this case. I think, yeah, usually they don't give you gravity, but it depends. So in this case, all we have to do is plug in 1.5 equals 2 pi square root of L over 9.8. And then we end up getting that L is equal to 0.56 meters. Okay, any questions on that? Okay, do you guys have any other last minute questions, concepts you want me to go over, things you're confused about, not sure about for your test? Yeah.
So for each, does our professor write the test, or does one, do they all write it together?
They all write different, as far as I know, they all write different tests, unless certain professors collaborate, but I think they're all different. Yeah, anything else?
Do you know if the other studies are we going with the same material or?
It's different material, we each write our own review.
Okay, thank you.
A little bit might be overlapping, but probably not much. Hugh has one tomorrow morning, 8 to 10. Yeah, sorry? Oh, okay.
If we do that one, it seems like a waste.
Yeah, we can do this one really quick. So, okay, so this one, so transverse waves travel with a speed of 20 meters per second on a string under a tension of 6 newtons. What tension is required for a wave speed of 30 meters per second on the same string? So, let's see if you recognize this formula. V equals the square root of TL over M. Have you seen that? No? Okay. Sorry. there's a lot of different formulas for this, but I would think that whichever ones you need for your exam, your professor would give you. I hope. I don't know. That's the best I can. Yeah. So for this problem, like you would pretty much need this one because then when you say like v1 over v2, the length is staying the same and the mass is staying the same, right? So that's essentially just going to be equal to T1 over T2. And then when you plug in like 20 over 30 is equal to square root of 6 over T2. And you find that T2 is equal to 13.5 newtons. Any questions on that? Yeah? I think that would be like the best way because most other because you need one that has tension in it, right? That's the only way like to find it, unless you went back and found some kind of acceleration with it. But this is the best way I can think of. It may be derived from finding like centripetal acceleration, like relating centripetal acceleration to like omega and like all that. But yeah. It's so like what we would get like after that is that root T1 L over M is equal to the square root of T2 L over M. And then you would get like the square root of like all of that, like so T1 L M over T2 L M. So these things would just cancel. No problem. Okay. So if any other last minute questions? If not, I would really appreciate if you guys would fill out the surveys. Yeah, I'll post the solutions tonight, hopefully, probably, if not, tomorrow morning. And yeah, Hugh will be here tomorrow, not in this room, but in a different room. And good luck to everyone. Yeah.
What's your bubble number?
I don't know. Just leave it blank. And then make sure you